increasing, decreasing, and their piecewise functions. Let's first start by determining the intervals on which the function is increasing, decreasing, and constant. Let's start with increasing. As the values from the x values from 3 to 5 are increasing, our y values are going from -2 to 2. So our x values are getting larger and our y values are getting larger. So my function is increasing from 3 to 5 because our values are getting larger. As x is getting bigger, our y values are getting bigger. Also notice that when I'm putting things in increasing and decreasing, that we're excluding our points because they're almost usually at a turning point. Also, our x values are increasing from -infinity to -1, but at the same time, our y values are decreasing. Also, our x values are increasing from 5 to +infinity, while our y values are decreasing. So our function, while our x values are increasing, our y values are decreasing, are from -infinity to -1 and from 5 to infinity. Notice that just because my arrow is pointing up does not mean that my equation is increasing or my function is increasing on this interval. Our y values are decreasing as our x values are increasing. This arrow just tells us that our graph continues in this direction forever. And where is our function constant? So as our x values increase from -1 to 3, our y values are remaining the same. So as our x values are increasing, our y values are remaining the same. So we are constant from -1 to 3. Notice that when I'm writing these intervals, I'm considerate about the x values that I'm placing on increasing, decreasing, and constant. Use Desmos to determine any relative maxima or minima of the function. F of x is equal to 0.1x cubed minus 0.6x squared minus 0.1x plus 2, and the intervals on which the function is increasing or decreasing. So within Desmos, I graphed our equation, and remember a couple videos ago we chatted about that Desmos puts these gray points at pertinent information. So we do have a relative maxima off to this left-hand side. This point right here would be 0.2, and the point just to the left of it is at -0.082. So this would be considered a relative maximum. It's not the extreme maximum, but it is a relative maximum. It's also known as a turning point. So the value of y is 2.004 when x is approximately -0.0082. We also have a relative minimum here, another turning point, and this turning point is at about -1.604 when x is about 4.082. We also have our function is increasing, decreasing, and increasing again. So these turning points are the points at which we change from increasing to decreasing and from decreasing to increasing. We'll talk about that in a few lessons ahead. So our equation is increasing from -infinity all the way to -0.082. And then it's also increasing again at about 4.082 through infinity. And then our graph is decreasing, starting at about -0.082, and it decreases until we hit the point 4.082. Two nurses, Kiara and Mateus, drive away from a hospital at right angles to each other. So we can say that this would be the hospital. Express the distance between the two cars as a function of time. Find the domain of the function. So we know that distance equals rate times time. We know that Kira's speed is 35 miles per hour and Mateus's speed is 40 miles per hour. So here's the hospital, here goes Kira, and here goes Mateus. One is driving 35 miles times how much ever time they're driving. And Mateus is going 40 miles per hour, so 40 times t. We don't know how long that they've been driving together. Well, we also know Pythagorean Theorem based on a right triangle. The distance between each other is the hypotenuse, and then each of the legs has the value of t. So we can find the distance set equal to 35t squared plus 40t squared. We know that to get rid of this this square, we can take the square root of each side. Well, when I take 35t squared, we have 1,225t squared, and 40t squared is plus 1,600t squared. When I add them together, we have 2,825t squared. Now taking the square root, and I'm placing t in absolute values because time cannot be negative. And since t represents time and it can't be negative, if we were to receive a negative value, which we can when we take the square root, we have to think about the positive and the negative value. By putting these absolute values here, we're assuming that t is going to be positive then. Is about 53.15 times how much ever time they are traveled apart. We also have to say that find the domain of the function. Well, we know that time can't be negative, so our domain has to be between 0 and infinity. Realistically, we're probably not going to drive forever, but we should put infinity since time does go forever. A community college has 30 feet of dividers with which to set off a rectangular area for a student testing center. If a corner of the math lab is used for the testing center, the partition needs only to form two sides of a rectangle. So here is the learning center itself, and then the testing center is this little corner. We only have 30 feet of dividers. Let's say that one side is x, then this other side would have to be represented by 30, since we only have a total of 30, minus whatever length this side is. So 30 minus whatever this length of this side is. And so and these two are covered by the wall, it says. So we only need to use 30 feet to cover these two pieces. Well, we can find the area then by taking 30 minus x times x. When doing so, we would then distribute, giving us 30x minus x squared. Let's find the domain of the function. Well, when I go ahead and graph this function and I zoom out using Desmos, I see then that my realistic domain is between 0 and 30 because I only have a maximum of 30 feet to use. When I graph this then, the high point is 15 to 25. So the dimensions of the maximum area, our relative maximum is 225 when our x value is 15, because we want to maximize this area. We want to use the most amount of area with those 30 feet of dividers. So we get an area then of 225 square feet when our x value is 15. So if our x value is 15 feet, I then can find, if this is 15, I then can find the length of this side by taking 30 minus 15. So the dimensions which would give us the greatest area would be a 15 foot by 15 foot area. In example 5 here, we're going to move on to talk about piecewise functions. Piecewise functions are interesting because they change the rules depending upon what part of the domain we are in. So in this particular example, we have 3 different parts of the domain. We have the domain when x is less than -2, when x is less than or equal, greater than or equal to -2, but less than or equal to 3, and then simply greater than 3. When I have a function value such as f of -5, -3, 0, 3, 4, and 10, I need to know where that x value falls within our set of functions to determine which one I need to use to evaluate. So when I look at f of -5 and -3, I see that they are both less than -2, so I'm going to use the first function for both of them. However, when I look at 0 and 3, they lie between -2 and 3 inclusive, so I'm going to use the second equation for when I plug in 0 and 3. And then finally with 4 and 10, those are both greater than 3. So I need to plug in 4 and 10 into our third equation in order to find the function value. So when I plug in -5 plus 1, we end up with -4. -3 plus 1 is -2. It really doesn't matter what I put in for 0 and 3 because my answer is always going to be 5, a constant function. And when I plug in 4 and 10, I get 4 squared, which is 16, and 10 squared, which is 100. We can also use Desmos to help us graph them. Notice how I'm writing this. I'm letting it be y equal to a condition semicolon the value itself. So I'm starting with the condition, putting a semicolon, and then putting the particular function value. And notice each one has its own line within Desmos. So let's see what that might look like once we graph. So I've got my graph here. I'm going to say y is equal to x is less than -2, semicolon, x plus 1. Putting in another one here, I'll shift over in a moment. -2. I need to use my toolbar to put the less than or equal to x, and then less than or equal to 3, and then semicolon 5. Close, and one more. Y is equal to x is greater than 3, semicolon, x squared, oops, and then close. So I have all my different values here. I've got my red, my blue, and my green. Now as I shift over my graph here so that we can see a little bit better, I'm going to zoom out. Notice, zoom out just a little bit more here. Okay. Notice and pay particular attention because we are not defined at -2 since our equation is only less than 2, not equal to -2. So although I don't see it until I click over it, note that it is an open circle there. We would expect on our constant line that our endpoints would be included because they have less than or equal to. So when I put my cursor over, I get equal to at the very ends as well, at 3 and at -2. And then finally, when x is greater than 3, I would also suspect that this would be also a open circle. So be careful when you're graphing your own that you're actually using open and closed circles as needed within your graphs. Let's take a closer look at another example. We have two equations here. We have when we are less than 3 or greater than or equal to 3. So at 3, the x value of 3, something's going to shift. Our graph is going to change its locations. So this first equation we know is going to be linear in nature. So we want to know specifically what happens less than 3 and at 3, knowing that at 3 will be excluded because it's less than. Our second equation is also linear, and we also want to know what happens at 3, but this time it's included, and then those values that are greater than 3. So I'm first going to start by plugging in some values which are less than 3, so I can get an idea of what my graph might look like. When I plug in -3, 0, and 2, I get our values, but I'm also going to plug in 3 as well. Because I know that when I plug 3 in, I'll end up with 1 plus 3, which is 4. But keeping in mind that 4 cannot be included. I can now start plotting these points. So we have the point 0, 3, and I also have the point 3, 4. But notice I have an open circle here because it's not included. Okay. So, and I know that all this linear line is going to keep continuing backwards forever and ever in this direction, so I could continue plotting those points as well. The next equation is x is greater than or equal to 3. So this time I know that 3 is included. And when I associate 3, I end up with -3. Plug in 4, we get -4. Plug in 6, I get -6. This time, notice when I plug in 3 and I get -3, I have a closed circle because it is included. And then I can continue plotting points so that I can create my line. We have 3 pieces to this next equation. We have 4 when x is less than or equal to 0. We have 4 minus x squared between 0 and 2. And then 2x minus 6 when x is greater than 2. Our first equation is a constant. In this particular one, we want to know what happens less than or equal to 0. Our second equation we know is quadratic, and we want to know what happens between 0, excluded, so we might want to put in an open circle, and 2, which would be included, a closed circle. And finally, our last equation is a linear equation, and we particularly want to know what happens greater than 2 in an excluded manner. Our first equation is constant, so it doesn't matter what we put in for x, it will always be 4. So notice between -infinity all the way to 0, I'm putting in y equals 4. By doing so, our point here would be included. Even though we don't see it, it would be included. Our next equation is 4 minus x squared. This would be quadratic in nature, so it doesn't surprise us that it's going to have a U-type shape to it. When I plot those points, then I also know that 2 is included. So 2 is included, so it has a closed dot at 2, 0. And then our linear equation, when we fill in the blanks, I know at 2 itself, if I had a value at 2 here, I would plug in 2, I would get 4 minus 6, which would be -2. So -2 has an open circle because at 2 it is excluded. But then I can use the rest of my points here to finish connecting the dots to create our linear equation. Graph the function as defined. We have the function f of x is equal to x squared minus 4 over x plus 2 for values where x is not equal to -2. And when x does equal -2, our value of y will be 3. So ideally, this piece here is just a single point. So when x is equal to -2, y is equal to 3. We plot our point here. The question is, what happens when x is not equal to -2? Well, notice that -2 cannot be in our domain, because if I were to plug in -2 for our denominator, we would end up with a 0. And we know that that can't happen. But what I can do is to simplify by factoring our numerator. This is a difference of perfect squares. A difference of perfect squares provides me with x plus 2, x minus 2. Go ahead and try foiling this or distributing this, and we'd end up back where we started. So I used the difference of perfect squares to factor this. Now notice then that if we have a common factor on our numerator and our denominator, these end up canceling themselves out, leaving us with just simply x minus 2 as our equation. We could then go ahead and plot our point -2, and our slope is up 1 over 1, because now we've created a linear equation. The only difference is that at the value of -2, we're going to have a hole, because we know in this particular equation we can't have x be equal to -2, so we just kind of skip that. There's a hole in our graph. So instead of our point being at -2, 4, it tells us in our function up here that our graph is really -2, 3 at that point. The last piece we need to discuss is a greatest integer function. These look kind of funny, but they're actually pretty cool. It's defined by many things, and notice it's going to extend negatively and positively forever and ever, because it's going to continue in this step direction. Although it doesn't appear so, our domain really is from -infinity to +infinity. Okay, so each value of x is certainly chosen and it has a y value to correspond to it. And our range is slightly different. So if we're going from left to right, we know that that talks about our domain, but up and down talks about our range. So notice that we always are skipping a value and we're going to the next whole number. So our range is -3, -2, -1, 0, 1, 2, and 3. And this concludes our lesson for this college algebra session.